This video covers the first section of Chapter 9 on inference for categorical variables. We're focusing on confidence intervals. We'll talk about the three different forms of inference. We'll talk about the difference between probability and confidence. We'll look at constructing confidence intervals. And we'll talk about how sample size affects levels of confidence. In the 4 stages of statistics, we're now in statistical inference, and we're talking about one categorical variable. So we're talking about a categorical variable, so let's review how we summarize a categorical variable. In the student survey, we can compute what proportion of students in the sample ate breakfast on the day of the survey. This is how we summarize the data for a categorical variable. We found that the sample proportion, p hat, is x over n. So remember that x is the count right there. X is the count. And n is the sample size, so that's 246 over 446, which is 0.55. So that's what we did back in part 2. Now that we're in part 4, what we're doing is going from the sample and trying to draw conclusions about the population. That's the notion of statistical inference. Now, there are 3 types of inference problems. Here's our situation with 446 students, 55% ate breakfast. So one type of problem is, let's make our best guess for what the population proportion is. If 55% of our sample ate breakfast, what would you guess would be the proportion in the population? We know that our guess isn't going to be necessarily correct. It could be off by a bit. So the second type of problem we'll look at is constructing an interval that should contain the actual true value of the proportion in the population, which we don't know. Finally, we can ask a question like this. Is the proportion in the population more than 50%? We could also ask a related question. Is the population proportion less than 60%? But those 2 types of questions are essentially the same, and we'll solve them the same way. Now, the first problem is what we're calling a point estimate. And you might guess that our best guess for the population proportion will be the same as the sample proportion. We'll talk more about that in a moment. For the second, we're talking about confidence intervals. At the end of this video, we'll introduce constructing confidence intervals. Finally, the third type of problem, in which we construct a hypothesis that the proportion, in this case, who eat breakfast is more than 1/2, and we test that hypothesis. So let's start with point estimates. Remember that p hat is a random variable for a fixed sample size n. The mean of the random variable p hat should be p, where p is the population proportion. Remember that this p here is a parameter because it comes out of the population. P hat, remember, is a statistic because it comes from a sample. So p hat is also considered a random variable. The mean of that random variable is p. We say that p hat is an unbiased estimator of p because it is equally likely to be high or low. In order for that to be true, the sample has to be random. So here's a problem, again from the student survey data. The sample proportion of intro to stat students at the university who'd eaten breakfast. Is this sample representative of all college students or of all students just at that university? Do you think the values of the variable, that is breakfast or not, are recorded without bias? Do you think that a person would have a reason to lie on the survey? So first, is the sample representative of all college students? Well, probably not, because from college to college, there'll be differences among cafeterias. There will be differences among residency rates. Some might live at home or in an apartment. some might live in a dorm. So it's safest in this case to just generalize to the population from which the sample was taken, and that is just the students at that university. Variable is not a terribly sensitive question. The variable here, whether you had breakfast, it's not controversial. I wouldn't expect people to lie to try to cover something up that they're embarrassed about. So let's look at a point estimate. In a representative sample of students, 55% ate breakfast. What is our best guess for the proportion of all students at that university who eat breakfast? Well, it's the only number we've got. P-hat is an unbiased estimator for P, so 0.55 is our best guess for P. Let's look more deeply at this example. Remember that our best guess for the population proportion is what we observed in our sample, 0.55. Do you think that the population proportion will be exactly 0.55? Or might we be a little bit off? If we might be a little bit off, by how much might we be off? Do we have enough evidence to conclude that the population proportion is greater than 1/2? Well, in the first question, no. Our sample was chosen randomly. We might have just by chance gotten an unusually high or unusually low number of people who ate breakfast. It's unlikely that it's going to be exactly what we see in our sample. To figure out by how much our guess is off, we're going to need more information, and we'll develop that over the next few slides. The last question we're going to save until the next section. So remember the three types of problems that we looked at before. We've talked about the point estimate. Now let's move on to the confidence interval. Remember that the proportion that you observe in your sample, as long as the sample is unbiased, will be our best guess for the unknown population proportion. When we're making this point estimate, notice that we didn't at all take into account the size of the sample or the spread in the sample. Knowing how far the data are spread out and how much data we have will play a role in how we answer the other questions. So let's start developing confidence. First, a quick word about the difference between probability and confidence. In the context of our problem, when we talk about probability, we're talking about a known, given population proportion, and we want to know how different samples might behave. On the other hand, the situation we find ourselves in now is one in which we don't know the population proportion. So that population proportion is not given. That moves us into the realm of confidence. When we're talking about confidence, in this case, we're given a sample proportion, and we want to know what the population proportion might be. Well, we can use the point estimate to get a guess, but what we're going to be more interested in is reporting a range of possible values. That range would be a confidence interval. So, here's an example. If students pick numbers from 1 to 20 at random, we would expect 5% to select each number. So let's focus on number 7. If we have a sample of size 400, I would expect p hat, which is the proportion in our sample, to pick number 7. The mean of p hat would be 0.05, and the standard deviation of p hat would be computed in this way. It's 0.01. This sample size is large enough that the shape of the distribution would be approximately normal. So what does the 95 part of the empirical rule tell us about p hat? Well, it tells us that 95% of the time, a sample of size 400 will have an observed proportion that falls within 2 standard deviations of the mean. That means between 0.03 and 0.07. Now, in this case, we knew what the ideal population looks like. We knew, in this case, P. Going forward, we may not know what that population proportion is, and we want to try to get information about it. So, here's another example. An instructor might say, I'm within 10 feet of a particular student. What can you say about where that student is in relation to the instructor? Doesn't it make sense that that student is also within 10 feet of the instructor? That brings us to margin of error. The margin of error is the distance around a sample statistic. That distance, that's like the 10 feet in the previous example, that distance is the distance that we expect the true value in the population to be away from our observed sample statistic. We'll commonly use 2 standard deviations for the margin of error. A confidence interval for the parameter is the interval within which we believe that the true value in the population, the parameter, will fall. That's our range of plausible values. Commonly, we'll use the sample statistic, that is like the sample proportion that we just saw, give or take 2 standard deviations. Do you see the relationship between margin of error and confidence interval? We see the margin of error here, and we see it again here. Now, notice that the parameter is not a random variable. In fact, it's not a variable at all. It's fixed. Since it is fixed, its value does not depend on a random process. That's the reason why we use confidence and not probability. So, let's say in our sample of 400, we actually saw 30 that picked number 7 as their random number from 1 to 20. If we assume that sample proportion for n equals 400 has standard deviation 0.01, what can we say about the population proportion who picked number 7? Well, we'll say that it's probably within 2 standard deviations of the observed value. So that would place it between 0.055 and 0.095. Now, because the value that we would expect to see, which remember was 0.05, if the selection was made completely at random, does not fall in our confidence interval, we'll think that perhaps our sample was biased in some way. That's why we have to say that we're pretty sure P is within 2 standard deviations of our observed value. So, pretty sure means that we are 95% confident. The way we interpret that as a probability is that the 95% would be the probability that any sample proportion that we take will fall within 2 standard deviations of the unknown P. Now, if we know the proportion in the population, we can say that the probability of getting a sample that's within 2 standard deviations of our known parameter, that's a probability statement. It's 95% of the time our sample will fall within 2 standard deviations of the parameter. When we don't know what the parameter is, we're talking about confidence. So we will say that we're 95% confident that the fixed but unknown P is within our interval. So focusing more on that notion of the difference between probability and confidence. If we know P in this case, if we know that the true value in the population is 0.05, right here, then what we can say as a statement about probability is that 95% of the time, P hat will fall between 2 standard deviations below and 2 standard deviations above that population proportion. So between 0.03 and 0.07. When we talk about a confidence interval for P, here we don't know what P is. We take our sample proportion, and then we produce a confidence interval for the unknown population proportion. Remember, we're not looking at a curve in this case because that population proportion is not a random variable. What we'll do is we'll take our sample proportion and we'll add and subtract the margin of error. That will create our confidence interval. Now, how is that margin of error determined? Well, remember, if we know what P is, the sample proportion will be centered at P. We'll have standard deviation square root of P times 1 minus P over N. Now, in this case, we're doing inference because we don't know what P is. And if we don't know what P is, that means we don't know what the standard deviation is. So we'll now define the standard error. The standard error is what we estimate the standard deviation of the sampling distribution to be. It's what we get when we use P hat in place of P in the formula for standard deviation. So if you're using the value in the population, if you're using P, what you're computing with this formula is standard deviation. If you're using a sample proportion, what you're computing is the standard error. This is a common technique that we will use. When we don't know something about the population, we'll substitute in the value in the sample. So the approximate 95% confidence interval for P is P hat, which is our estimate for the value in the population, plus or minus 2 standard errors. Remember, P hat is our point estimate, and the square root of P hat times 1 minus P hat over N is the standard error. To get the 95% confidence interval, we'll go up and down by 2 of the standard errors. That will generate our 95% confidence interval. Now, under what conditions will this formula work for the 95% confidence interval? Well, we need a few things. First, the sample has to be unbiased, because if the sample is biased, it's going to pull P hat in one direction or the other, and that's going to throw off our interval. Next, N has to be big enough so that P hat is approximately normal. Otherwise, we can't use that 2 that we get from the 68, 95, 99.7 rule to generate the interval. We also need to know that the population size is at least 10 times N, which, remember, guarantees that our selections are approximately independent. So let's look at this second criterion. That multiplier of 2 that comes from the normal distribution requires that N times P and N times 1 minus P are both at least 10. But remember, we don't know what P is, but we're using P hat as our substitute for P. So we will need N times P hat, which, remember, is just the count in our sample, to be at least 10. And we need n times 1 minus p, which is n minus our count. In other words, x is the number in our sample that fall within the category that we like. N minus x is the number that don't fall in the category that we like. So the sample count in the category and the sample count that is not in the category both need to be at least 10. Now, in the example where we had 30 out of 400 students picking the number 7 at random from among the numbers from 1 to 20, do we have enough data to satisfy the requirement that the distribution for sample proportion be approximately normal? Yeah, because 30, that's the actual count in our category, and 370, which is the count outside our category, are both at least 10. Now let's check population size. In this example, we want to draw conclusions about criminal histories of a city's bus drivers. Of the 750 bus drivers, a random sample of 100 drivers was selected. Do we have approximate independence? No, because the population size, 750, is not at least 10 times the sample size of 100. So the computations that we make are not going to be terribly accurate. So back to the breakfast question. Remember that we had 55% of our sample of 446 college students eating breakfast the morning of the survey. Assuming this is a representative sample, what would be the correct confidence interval for the proportion of all students at that university who eat breakfast? Well, the 95% confidence interval for P would be the center, which would be 0.55, plus or minus 2 standard errors. That's 0.55 plus or minus 2 times the square root of 0.55 times 1 minus 0.55 all over 446, which gives us an interval from 0.51 to 0.59. Now, remember, one of the questions that we asked was whether the proportion of students in the population, that is all the students at the university, whether of all of those students, if more than half would eat breakfast. This 95% confidence interval gives us pretty strong evidence for that claim, because 0.5 is not in that interval. So let's take a look at the role that sample size plays in computing confidence intervals. If we're looking for a 95% confidence interval based on a sample proportion of 0.54 with 3 different sample sizes, 50, 200, and 1000, look at what happens as n increases. When n is 50, the confidence interval goes from 0.4 to 0.68. But as n goes up, the confidence interval shrinks. Notice that 0.54 is right in the center of all 3 of these intervals. It's the margin of error that's going down. When you see polls in newspapers or on television, one of the most frequent margins of error you'll see is plus or minus 3%. Why? Because if you look at these 3 different possible values for n, you'll see that a margin of error of 3% corresponds to a sample size of about 1,000. Now, there's nothing special about 95%. We could also compute a 90% confidence interval, a 98% confidence interval, or a 99% confidence interval using these different z values as our multipliers. So if you want to use want to report a 98% confidence interval, you'll use a multiplier of 2.326. That's because under the normal distribution, 98% of the area falls between z-scores of negative 2.326 and positive 2.326. If you want to be more precise about your 95% confidence interval, you'll use 1.96 instead of 2. Here's an example. If we've got a sample of size 108, these are students in committed relationships, 70% said they took comfort by smelling their out-of-town partner's clothing. If we compute the standard error, we get something around 0.04. So what do the 90, 95, 98, and 99% confidence intervals look like? The 90% confidence interval would be 0.7 plus or minus 1.645 times the standard error, which gives us a confidence interval from 0.63 to 0.77. We'll do something similar for the others. And we see that as confidence goes up, the width of the confidence interval also goes up. That's because these multipliers are getting bigger as the confidence interval gets bigger. So looking at this graphically, as the level of confidence goes up, the width of these confidence intervals also goes up. The more confident we want to be, the wider our confidence interval has to be. So we are less confident about a small interval, and we are more confident about a wide interval. Let's talk about using technology to find confidence intervals. On your calculator, we'll find confidence intervals for proportions under the Stat menu. We'll go over to Tests, and what we're looking for is an interval. There are lots of these as you scroll down, but what we're looking at here involves a proportion, and a single proportion. So what we want is, here in mine it's option A, the one proportion z interval. So let's go select that one proportion z interval. And now our calculator is asking us for three things. It's asking us for x, that's the count. It's asking for n, that's the sample size. And it's asking us for the confidence level. So in one of the examples we saw earlier, we saw that 30 people out of a sample of 400 selected 7 as a random number between 1 and 20. Let's compute a 90% confidence interval for the actual proportion in the population that would select 7 as their random number between 1 and 20. So I've entered 30 in for x because that's the count in my sample. I've entered 400 for n because that's the sample size. And I've entered 0.90 for sea level because I want a 90% confidence interval. I'll select Calculate, and I see the interval 0.05334 to 0.09666. The calculator also computes p hat for me. You see it there, it's 0.075, and it reports the sample size as well. When we look at confidence intervals in the long run, if I flip a coin 20 times over and over and over again, and based on each result I get, set up a 95% confidence interval for proportion of heads. This gives me a way that I can interpret that 95% confidence as a probability. In the long run, if I do this over and over and over again, 95%, that's 19 out of 20, of the confidence intervals I construct should contain the true population proportion. So, If on the first time I do this, I flip 9 out of 20 heads, that's 45%, and I construct the 95% confidence interval. Sure enough, it contains 1/2. And then I do it again. I get 8 heads. That's a a sample proportion of 0.4. I construct the confidence interval, and it's also good. I do it again. I get 12 heads, compute that confidence interval, and sure enough, 0.5 is in there. But let's say I do it again, and I get unusually lucky. I end up with 15 out of 20. If I compute the 95% confidence interval there, whoop, there I see my confidence interval does not contain 0.5. And I keep doing this, and I keep doing this, and I keep doing this. Overall, in the long run, 95% of the intervals that I construct will contain 1/2. 5% of the intervals will not. That's how we interpret that 95% confidence. So here's an example. Quote, President-elect Barack Obama's campaign strategists weren't the only ones vindicated Tuesday. Pollsters came out looking pretty good too. Of 27 polls of Pennsylvania voters released in the campaign's final 2 weeks, only 7 missed Obama's 10.3-point victory by more than their margins of error. Obama's national victory of about 6 points was within the error margins of 16 of the 21 national polls released in the final week. Does this really vindicate pollsters? That's a 75% success rate. If we're using 95% as our level of confidence, we ought to see 95% of those hitting their mark within the margin of error. So, to wrap things up, we looked at the 3 different ways that we can ask a question about inference. In this lecture, we focused on constructing confidence intervals. We talked about the difference between probability and confidence. We talked about how to construct a confidence interval by finding the margin of error, which is computed based on the standard of error, the conditions under which we can use that formula. We talked about how an increasing sample size makes the confidence intervals smaller. We talked about how to compute confidence intervals at other levels. And we talked about interpreting that confidence interval over the long run.